types of reactions, I kind of combined them into the three sections. 4.7, we already did the precipitation reactions. That was in like net ionic 4.2. Here, I'm incorporating it in with that 4.8 because that's all about acid-base stuff. So we're going to do that acid-base part of the types of reactions here. And then the redox one we'll do with the redox section as well. So basically, what are we talking about here when we're talking about acids and bases? We're going to be looking at identifying an acid-base reaction, identifying species as Bronsted-Lowry acids, bases, conjugate acid-base pairs, and this is based on proton transfer involving those species. And then we're going to compare relative strengths of conjugate acid-base pairs based off of ionization. All right, so starting with the most basic model or definition of acid bases. And this is probably the only time you'll hear about the Arrhenius definition. Basically states that an acid is any species that produces hydrogen or hydronium in solution in water. Okay? Now, we're going to talk about hydronium in detail a little bit in a minute because hydrogen doesn't really exist as free floating. It is actually attached to the water molecule as shown in this particular diagram. Bases though, Arrhenius bases are ones that produce hydroxide in solution. Now let's not get hydroxide confused with hydroxyl groups. Hydroxide is an ion. It's like KOH or NaOH. It's attached to metal or it's attached to ammonium like so. These are the ones that form hydroxide in solution are going to be your strong bases. Don't get that confused with alcohols where you have the OH groups on the carbon molecules. Those OH groups around the carbon molecules are part of alcohols or carboxylic acids and they do not detach. Okay? So they're not the same thing as hydroxide. Hydroxides you'll always see with the metals or ammonium. And then you know that's in the base category. If you see OH groups on organic molecules that have carbon and hydrogen, you know that those are not going to detach, and those are called hydroxy groups. They're the ones that do the H bonding. They're a little bit separate, different category. But bases, hydroxides drive up the pH, okay? Higher concentration of hydroxide versus higher concentration of hydrogen. Now, let's talk about hydronium. Hydronium is actually what happens in water. Free H plus ions do not exist in water. Instead, they attract to the water molecules and form H3O plus. H3O plus then is interchangeable with H plus in acid-base problems. So some acid-base problems will just call it H plus, some acid-base problems will call it H3O plus. Either way, it means the same thing. So remember that hydrogen ions, H plus, in and of itself is just a proton. Hydrogen has one proton, one electron, so if you lose the electron, there's only the one proton left. That little tiny proton gets attracted into the water's electron clouds and therefore incorporates and becomes hydronium. It doesn't just sit around floating free by itself. So, what does hydronium look like? It is a pyramidal shape. It's got the three bonds with the H's and the lone pair on the top. And it forms this cation, this polyatomic cation. Now, there is not a lot of polyatomic cations out there, but hydronium is one of them. The other one that we look at and use a lot, especially in acid-base chemistry, is ammonium, NH4+. So you'll see that one out and about here in this unit as well. But there aren't a whole lot of polyatomic ions that happen to be positive. This one just is one of them, one of the few. Now, the one definitions and models we're going to look at in more detail and use more in AP is the Bronsted-Lowry definition. Bronsted-Lowry, where acids are H plus donors, they give them away, and bases are the ones that accept the H pluses or the protons. Now, water has the ability to do both. Water can donate an H and water can accept an H. So we say water is a chemical species that is amphoteric. So if you're looking here at our example diagram of how this transfer might occur, it is you need to have two things in order for it to occur, because one has to donate, one has to accept. So if we're looking at the reaction of putting ammonia in water, ammonia is the base and water is going to act as the acid. So that means that the water is donating the H over to the ammonia. When it does that, it loses an H and it becomes hydroxide. You lose an H plus, you go down one in charge as well, because water is neutral. You lose the H plus, it now has a minus charge. The ammonia gains the H plus and becomes ammonium. Once again, if you're gaining an H plus, you go up one in charge. So instead of being NH4, it's now NH4 plus, gains the H plus and adds that over. But as you can see, it is a paired deal. The acid and the base are on the left over here as the reactants. The conjugates are on the right as the products. And they are paired together, as you can see here in this particular diagram. So let's talk about conjugate acid-base pairs. I'm sorry, there is a typo here. I don't believe it's in the notes, but this is supposed to say HA, like so. And I use A as generic anion, okay? Conjugate base is the acid molecule that lost the one proton, okay? The conjugate acid is going to be the base that gained the one proton. And then, of course, amphoteric doesn't only apply to water. It can be any species that can accept or donate a proton. But in this particular case, the acid here, H, that's going over here to the water. When it does that, it forms hydronium, H3O+. And you're left with only the anion over here, A-. The anion is the conjugate base. So, acid base on the left, reactants, conjugates are on the right. They are paired together. The HA and its conjugate is going to be A-, so the acid and its conjugate base. The water is the base, and hydronium is the conjugate acid. That's the pair there. Like so. So now we're going to practice. We're going to look here at making the conjugate acids and bases for these amphoteric substances. So if we're going to the conjugate acid side, what are we doing? Are we adding the H or taking away the H? To the conjugate acid? Forming the acid, yes, you're going to be adding the H plus. If you are going to the conjugate base, you would be removing the H plus, right? Oh, yes, I forgot the subtraction part, you're right. So here you would be minusing the H plus, there you go. And then it's really follow the H. If we add an H to H2O, which is neutral, that means it's going to become H3O plus, right? You have to add one to the charge there because the H brings in a plus charge. If we take away the H though, we are just left with OH or hydroxide, and it was neutral. Now we took away a positive, it is now down one on the charge. Okay, so add the H, go up in charge by 1, take away the H, go down in charge by 1. So if we're doing here for the HSO4, that is called bisulfate or hydrogen sulfate. What would be the conjugate base of that one? the conjugate base. SO4, right? We took away the H, and what happens to our charge?
It goes down, so it's on
-2, very good. Over here on the left, if we're going to the conjugate acid of HSO4 minus, add the H, so we get, all right, now bicarbonate, HCO3 minus, which is the part of sodium bicarbonate. If we go to the conjugate base over here, it's just going to be CO3, and then the charge goes up by, goes negative by 1, so -2. Added over here, we get H2CO3. Adding the H versus removing the H. And then the last one here with dihydrogen phosphate. The conjugate base is
the -2 charge.
good. And then if we add the H over and make the acid.
H3PO.
Now I'm going to qualify something for you so you know how many H's can you add. There's only a couple species that can go into the plus direction, like hydronium is H3O plus. It can go in the plus direction. Another one is going to be ammonia, right? You have ammonia, you add an H plus, you can get ammonia. We have our 2 cation ions here. These are pretty much the only ones that will go above neutral. Any of these other ones, when you get to neutral, you can't keep adding H's to it. It just doesn't exist in nature. You can keep taking off the H's until you're down to no H's, but once you get to neutral on the acids over here, you would stop. You can't add another H to this and make it H3OSO4 plus. Like that does not exist. Can't go above neutral on those.